The universe has been expanding for approximately 13.8 billion years. Every distant galaxy is moving away from us. Every year, the space between galaxies grows larger. It is easy to assume that this is simply how the universe works, but expansion is not a law. It is a condition, and conditions can change. The Big Crunch is not science fiction or a forgotten idea from the early days of cosmology. It is a mathematically valid solution to Einstein's field equations, the very same equations that predicted black holes, gravitational waves, and the expansion of the universe long before any of them were observed. If that solution is correct, then one day every galaxy will stop moving apart. Expansion will end, gravity will take over, and everything that has ever existed will begin falling back toward everything else. The observable universe stretches across approximately 93 billion light years today. In a big crunch, all of that space could collapse until every star, every planet, every black hole, every atom, and every trace of every civilization occupies a region smaller than a single proton. The temperature of space is currently just 2.725 Kelvin, only a few degrees above absolute zero. During a big crunch, that temperature would reverse direction, climbing toward values so extreme that the known laws of physics can no longer describe what happens next. Some cosmological models suggest that the moment expansion finally gives way to collapse may begin far beyond the edge of the observable universe, in regions whose light has not yet had time to reach us. If that were true, we would have no way of knowing until the evidence arrived billions of years later. The most unsettling part is that the entire fate of the universe may depend on a single number that scientists are still trying to measure with complete confidence. If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. Now, let's begin. We inherit a universe already filled with galaxies, stars, and distant light, making it easy to forget that every one of those things had a beginning. If we travel backward through that immense history, the familiar landmarks steadily disappear. Galaxies dissolve into simpler structures. Stars fade from existence. Even the first atoms eventually vanish from the story, leaving behind a cosmos that grows stranger with every imagined step. Today, we know the universe is about 13.8 billion years old because its earliest surviving light still surrounds us. That ancient glow is called the cosmic microwave background, the faint afterglow released when the young universe first became transparent. It has crossed unimaginable distances ever since, carrying a remarkably detailed record of conditions that existed when everything was still in its infancy. Before that moment, there were no stars to illuminate space, and no planets waiting to form. Matter existed in an intensely energetic state, where electrons could not remain attached to atomic nuclei. Light scattered constantly from particle to particle, leaving the entire universe wrapped in an opaque plasma. Nothing could travel freely, nothing could reveal the wider landscape. Earlier still, during the first fraction of a second, the universe experienced inflation, an astonishing episode in which space itself expanded at an extraordinary rate. This was not ordinary motion through space. Space stretched, carrying every newborn region away from every other. Distances increased so rapidly that areas once unimaginably close became separated across enormous scales. Only a few minutes after the beginning, temperatures had already fallen enough for protons and neutrons to combine into the first nuclei of hydrogen and helium. These simple ingredients became the raw material for everything that followed. Yet countless ages passed before complete atoms could finally emerge as electrons settled into stable orbits around those nuclei. the universe changed forever. Once light could move without constant interruption, the long era of darkness gradually gave way to new possibilities. Roughly 200 million years later, the first generation of stars ignited. These enormous objects, known as population 3 stars, burned with extraordinary intensity before ending their brief lives. Inside their blazing interiors, heavier elements formed, enriching the surrounding universe with the building blocks that future stars, planets, and eventually living creatures would require. Galaxies slowly gathered under gravity, merging, growing, and weaving the immense cosmic web we observe today. Expansion continued through every stage of that journey, but expansion itself is simply the present behavior of the universe, not an eternal promise. That distinction matters. As we continue together, you can begin to see why the greatest question in cosmology is remarkably simple beneath all its complexity, which influence ultimately proves stronger, the outward motion born at the beginning, or the patient pull of gravity that has never stopped reaching across the cosmos. That's writes the final chapter, long before any civilization is there to read it. Sometimes the greatest discoveries begin with nothing more dramatic than careful measurement. While examining distant galaxies during the late 1920s, astronomer Edwin Hubble noticed an astonishing pattern hidden inside their faint light. Every galaxy he studied appeared to be moving away from our own. The farther a galaxy stood from us, the faster it seemed to recede. That simple relationship transformed our understanding of the cosmos forever. At first glance, it sounded almost impossible. Were galaxies racing outward from a central explosion through empty space? But the answer proved even more remarkable. Space itself was expanding. Imagine raisins inside rising bread dough. As the dough swells, each raisin sees every other raisin moving farther away, even though none of them are actively crawling through the dough. We occupy one of those cosmic raisins, watching the fabric around us stretch in every direction. This relationship became known as Hubble's law, a mathematical description linking a galaxy's distance with its recession speed. The farther away a galaxy resides, the greater its apparent velocity. Scientists summarize this behavior using the Hubble constant, a value describing how quickly space expands across immense distances. Its commonly accepted value is about 70 kilometers per second for every megaparsec, meaning that over a distance of 1 megaparsec, which equals about 3,260,000 light years, the expansion adds roughly 70 kilometers of separation each second. But another puzzle soon appeared. Modern astronomers measure the Hubble constant using two highly accurate techniques. One method studies nearby stars and exploding stellar remnants to build a cosmic distance ladder, a sequence of overlapping measurements that extends farther into space. The other examines the cosmic microwave background, allowing researchers to calculate the expansion rate from conditions in the infant universe. Both methods are precise, yet they disagree by enough to trouble cosmologists. This disagreement is known as the Hubble tension. A tension in science means two reliable results refuse to match despite repeated testing. The instruments continue improving. Independent teams repeat their work. The discrepancy remains. Perhaps an unknown measurement error still hides within the data. But many physicists suspect the universe may be revealing new physics that current theories cannot yet explain. Long before these observations, many scientists believed the universe neither expanded nor contracted. Even Albert Einstein expected an eternal and unchanging cosmos. To preserve that expectation, he introduced an additional mathematical term into his gravitational equations, designed specifically to hold the universe steady against collapse. When Hubble's observations demonstrated ongoing expansion, Einstein reportedly described that adjustment as his greatest blunder. But the discovery carried another profound implication. If expansion could begin, then perhaps it could also slow, halt, and even reverse under the influence of gravity. We now recognize the expanding universe as an evolving process rather than a permanent condition. That realization changed cosmology forever, inviting you and me to view the history of the universe as a story with an opening chapter and perhaps a final one. Imagine placing the entire universe onto a perfectly balanced scale. On one side rests every form of matter and energy pulling inward through gravity. On the other lies the momentum of expansion, carrying galaxies farther apart with the passage of time. Cosmologists have found a remarkably elegant way to describe that balance. They call it omega, a quantity known as the density parameter, because it compares the universe's actual average density with the precise density required to halt expansion. This comparison is deceptively simple. If omega is greater than 1, the universe contains more than enough matter and energy for gravity to overcome expansion eventually. The outward motion slows across immense stretches of time until it finally stops. From there, the entire cosmos begins contracting toward a future known as the Big Crunch. But another outcome exists. If omega equals exactly 1, the universe is considered geometrically flat. A flat universe does not collapse, yet it never completely escapes gravity either. Expansion continues forever while gradually slowing, producing an aging cosmos that becomes colder, darker, and increasingly diffuse across unimaginable spans of time. There is also a third possibility. If omega falls below 1, the average density remains too low for gravity to reverse the expansion. Space continues growing larger without ever turning back. Depending on how another cosmic ingredient behaves, that future could end in an immense frozen emptiness or an even stranger destiny where expansion accelerates until large structures themselves are eventually pulled apart. Modern observations place omega astonishingly close to 1. That result is both encouraging and deeply frustrating. The measurements suggest a universe balanced with extraordinary precision, yet they have not revealed whether the true value sits just above or just below that critical dividing line. The uncertainty is incredibly small. The consequences are enormous. To appreciate this balance, consider the critical density itself. It equals roughly 9.47 multiplied by 10 raised to the negative 27th kilograms within every cubic meter of space. A cubic meter is simply a box measuring 1 meter along each side. Averaged across the entire universe, that amount corresponds to only about 5 hydrogen atoms occupying the same volume. Now compare that with the air surrounding you. A single cubic meter of ordinary air contains roughly 2.7 multiplied by 10 raised to the 25th molecules. The contrast is almost beyond intuition. The average universe is staggeringly empty, yet even that sparse distribution determines the destiny of everything that has ever existed. But gravity accumulates patiently across vast distances. Every galaxy, every cloud of gas, every unseen source of mass contributes another tiny pull. When added together over the entire cosmos, those countless contributions determine whether expansion remains victorious forever or eventually reaches its limit. In the end, the future may depend upon a difference so slight that our finest instruments are still striving to measure it with complete confidence. Stand beneath a clear night sky, and everything you can see belongs to a surprisingly small fraction of reality. Every glowing star, every luminous galaxy, every drifting cloud of gas, every planet, and every living world together account for only about 5% of the total contents of the universe. The remaining cosmic inventory hides beyond ordinary sight, shaping the universe without revealing its own nature. The largest unseen portion relevant to gravity is called dark matter. The name describes what astronomers observe rather than what they understand. It neither emits light nor reflects it. It does not absorb light in any measurable way, and it appears to avoid interactions with electromagnetic forces entirely. Yet, its gravity leaves unmistakable fingerprints across the cosmos. The first major clue emerged during the early 1930s when astronomer Fritz Zwicky studied the Coma Cluster, an enormous gathering of galaxies moving together through space. He calculated the visible mass contained within the cluster and compared it with the tremendous speeds of its member galaxies. The numbers refused to agree. The galaxies were traveling so rapidly that the cluster should have dispersed long ago. Something unseen supplied the additional gravity needed to hold everything together. But the mystery deepened decades later. During the 1970s, astronomer Vera Rubin carefully measured how stars orbited within spiral galaxies. According to ordinary gravity, stars far from a galactic center should move more slowly because most visible matter lies closer to the middle. Instead, the outer stars traveled almost as rapidly as those much nearer the core. Their orbital speeds remained unexpectedly high across enormous distances, revealing that an invisible halo of mass surrounded each galaxy. Those observations transformed astronomy. Dark matter became the best explanation for the hidden gravitational framework, supporting galaxies and even larger cosmic structures. We now believe vast halos of this invisible substance envelop galaxy clusters, preventing them from flying apart while guiding the growth of the immense cosmic web. Yet the identity of dark matter remains unknown. Among the leading possibilities are weakly interacting massive particles, hypothetical particles that possess mass while rarely interacting with ordinary matter, and axions, extremely light particles proposed to solve another puzzle within particle physics. Despite decades of increasingly sensitive experiments, neither candidate has been directly detected. But this mystery reaches far beyond particle physics. It also influences the possible fate of the universe itself. Every unseen reservoir of dark matter contributes additional gravity to the cosmic balance discussed earlier. As more mass accumulates, the value of omega inches upward toward the critical threshold, separating endless expansion from eventual collapse. That is why astronomers continue searching with such determination. If future observations reveal that dark matter is more abundant than current estimates suggest, gravity gains additional leverage across the largest scales imaginable. A difference almost impossible to notice within a single galaxy could become decisive when measured across the entire universe, slowly tipping the balance toward a future where expansion ultimately surrenders to the long, persistent pull of gravity. For much of the 20th century, astronomers expected gravity to behave exactly as common sense suggested. Expansion should continue after the beginning, yet every galaxy would gradually lose speed as the combined gravity of the universe pulled against that motion. The only remaining question seemed to be how quickly expansion would slow. Few imagined that the opposite answer awaited them. Everything changed during the late 1990s when two independent, international research teams examined a special kind of exploding star known as a Type 1a supernova. These stellar explosions shine with remarkably consistent brightness, allowing astronomers to compare how bright they appear with how bright they truly are. That comparison turns them into dependable cosmic distance markers stretching across billions of light years. The observations refused to cooperate with expectation. Instead of finding a universe whose expansion was gradually weakening, both teams discovered that distant galaxies were separating from one another at an ever increasing rate. The farther into cosmic history they looked, the more clearly the acceleration emerged. At first, several researchers suspected hidden errors in their calculations or observations. They checked the data repeatedly. The conclusion remained unchanged. Something unknown was pushing the universe apart. Scientists gave this mysterious influence the name dark energy. The term does not describe a visible substance or a conventional force. It simply labels the unexplained phenomenon driving accelerated expansion across the largest scales imaginable. Current measurements indicate that dark energy accounts for roughly 68% of the total energy content of the universe, making it the dominant ingredient in the cosmic inventory. But its origin remains deeply uncertain. The leading explanation is called the cosmological constant. This idea proposes that empty space itself possesses an intrinsic energy, meaning that even a perfect vacuum contains energy woven into the fabric of space. According to quantum field theory, the framework describing the behavior of fundamental particles and fields, empty space is never truly empty. Tiny virtual particles continually appear and disappear for incredibly brief moments, creating restless activity throughout the vacuum. Here the story becomes even stranger. When physicists calculate the vacuum energy predicted by quantum field theory, the result exceeds the observed value by roughly 1, followed by 120 zeros. This astonishing mismatch is known as the cosmological constant problem, widely regarded as the largest disagreement between theory and observation anywhere in modern physics. For the Big Crunch, this invisible energy presents the greatest challenge. As long as dark energy remains constant or grows stronger, accelerated expansion continues, carrying galaxies ever farther apart despite gravity's persistent pull. Under those conditions, collapse never begins, but certainty still escapes us. Nothing yet proves that dark energy must remain unchanged forever. If its strength slowly weakens across the immense lifetime of the universe, gravity steadily regains influence. The balance shifts almost imperceptibly at first, yet over billions of years that subtle change could transform the ultimate fate of everything we have explored together, allowing the possibility of cosmic contraction to return from speculation toward genuine scientific consideration. Among all the numbers used by cosmologists, one of the most influential is represented by a single letter, pronounced simply as W. This quantity is known as the equation of state parameter, a value that compares the pressure of dark energy with its energy density. In plain terms, it tells us how dark energy behaves as the universe grows. A tiny change in this number could reshape the entire future of the cosmos. If the value of W is exactly -1, dark energy behaves as a true cosmological constant. Its strength never changes. As space expands, the influence of dark energy remains steady, continuing to drive galaxies farther apart across unimaginable spans of time. This picture forms the foundation of the current standard model of cosmology. But nature may not choose such perfect simplicity. Suppose the value falls below -1. In that case, physicists describe the phenomenon as phantom energy. The name reflects behavior that appears almost impossible. Instead of maintaining constant strength, this form of dark energy becomes increasingly powerful as the universe expands. Every passing age gives it greater influence over the fabric of space itself. The consequences would be extraordinary. Expansion would accelerate beyond anything expected from a stable cosmological constant. Galaxy clusters would gradually lose their gravitational grip. Individual galaxies would eventually come apart. Much later, solar systems would no longer remain bound to their stars. Planets would drift away. In the final stages, even atoms could no longer resist the relentless stretching of space. This scenario is known as the Big Rip because every level of cosmic structure ultimately comes undone. But another possibility remains equally fascinating. If the value of W lies slightly above -1, dark energy gradually weakens instead of strengthening. Gravity, which has patiently acted throughout cosmic history, slowly recovers some of its influence. Expansion continues for an immense length of time, yet its dominance is no longer guaranteed. Under those conditions, the path toward a future contraction returns to scientific consideration. Current observations have not resolved this question completely. Measurements from the Planck satellite indicate a value close to -1.03. The uncertainty surrounding that measurement remains important because the allowed range still includes values slightly above -1. The difference appears almost insignificant, yet it separates dramatically different destinies for the universe. That uncertainty has become one of the most active frontiers in modern cosmology. Researchers continue refining observations with increasingly sophisticated instruments, searching for subtle changes that earlier surveys could not detect. Every improvement narrows the possibilities. During the year 2024, the first major results from the Dark Energy Spectroscopic Instrument introduced another intriguing development. After mapping millions of galaxies and distant quasars, the observations suggested that dark energy may not remain perfectly constant through cosmic history. Instead, its influence could be evolving over time, perhaps becoming weaker as the universe ages. The evidence remains preliminary and requires independent confirmation, but it reminds us that the final verdict has not yet been written. The future of the universe may rest upon a quantity so delicate that we are only now beginning to measure it with the precision it demands. There is no great flash announcing the turning point. No universal alarm echoes across the galaxies. If the big crunch truly belongs to our future, the transition begins with extraordinary restraint, unfolding across spans of time so immense that even advanced civilizations could mistake it for permanence. The universe simply approaches a moment cosmologists call the turnaround, the instant when expansion finally reaches its greatest extent. At that moment, the cosmos has achieved its maximum size. Every galaxy that has spent billions of years drifting farther away reaches the end of that outward journey. Expansion falls to zero. Then, almost imperceptibly, the direction changes. Distances that had steadily increased for ages begin shrinking instead, and the long return quietly begins. But nothing dramatic happens within an individual galaxy. Stars continue circling their galactic centers. Planetary systems follow familiar orbits. Atomic processes remain unchanged. If you lived inside a distant galaxy during the earliest stages of the turnaround, daily existence would appear completely ordinary. Local gravity already governs those nearby structures, so the reversal of expansion across the wider universe would initially leave them untouched. Only patient observation could reveal the truth. Astronomers comparing the motion of extremely distant galaxies across vast intervals of cosmic time would gradually notice recession speeds becoming smaller than expected. These recession velocities describe how rapidly galaxies move away because space itself expands between them. Detecting such subtle changes would require generations of measurements, each more precise than the last, gathered over astonishing lengths of time. But another limitation makes the turnaround even more elusive. The universe reveals itself only through light, and light requires time to travel. If distant regions crossed the turnaround before our own neighborhood, we would remain unaware until their light finally reached us. That delay could span millions or even billions of years, depending on the distances involved. The event itself and our knowledge of it would never arrive together. Current cosmological models placing a big crunch within the realm of possibility usually predict the turnaround tens of billions of years ahead. Some more compressed scenarios allow it to occur after only a few billion additional years, although those models remain far less favored by present observations. The uncertainty reflects how much still depends upon the evolving behavior of dark energy and the total density of the universe. Once the turnaround is complete, the balance governing cosmic evolution changes profoundly. Gravity no longer struggles against an expanding background. Instead, it becomes the dominant influence across every scale of the observable universe, guiding the motion of galaxy clusters, enormous filaments, and vast regions that have spent almost the entire age of the cosmos moving apart. The reversal begins with extraordinary patience. Yet from that single transition, every later stage of cosmic contraction follows naturally, each unfolding according to the same gravitational laws that have quietly shaped the universe since its earliest moments. Imagine returning to the same stretch of sky after countless ages have passed. At first, you would struggle to notice anything different. The familiar galaxies would still occupy distant corners of the heavens. Stars would continue orbiting within their galactic homes, and planetary systems would follow the same dependable paths they always had. The earliest phase of contraction hides behind an appearance of remarkable normality. Yet careful measurements would begin revealing a subtle change. For billions of years, astronomers relied on redshift, the stretching of light toward longer wavelengths, as evidence that distant galaxies were moving away because space itself expanded between them. During the opening stages of contraction, that pattern would slowly lose its dominance. More and more galaxies would display blue shift instead, a shortening of light waves showing that they were drawing closer rather than receding. This transformation would not occur all at once. The number of galaxies exhibiting redshift would gradually decline, while the population displaying blue shift steadily increased. What had once been an unusual observation beyond our own local galactic neighborhood would eventually become the universal rule. Every distant direction would begin telling the same story. The cosmos had reversed its overall motion, but light itself would also reveal another profound change. The cosmic microwave background, the ancient radiation left behind from the universe's earliest transparent era, has spent billions of years stretching into longer microwave wavelengths as space expanded. Once contraction begins, that process reverses. Those wavelengths slowly shorten. The radiation shifts toward higher energies, beginning a gradual journey away from the microwave portion of the spectrum. Its temperature changes as well. Today, the cosmic microwave background measures approximately 2.725 Kelvin, only a little above absolute zero. During contraction, that temperature begins rising. At first, the increase is extraordinarily slow, requiring billions of years before becoming obvious. As the universe continues shrinking, the warming accelerates, reflecting the growing concentration of radiation throughout space. Meanwhile, galaxies that had spent roughly 13 billion years drifting apart begin an equally long return toward one another. The immense architecture of the cosmos responds with remarkable patience. Vast filaments containing countless galaxies slowly draw inward. Gigantic walls of matter become more compact. The enormous voids separating these structures gradually lose their emptiness as distances steadily decrease. None of this brings immediate catastrophe. Any civilization living within a stable galaxy during these early ages would experience no sudden physical danger. Stars would continue shining, planets would remain in orbit. Life, if present, could endure for spans that still dwarf the entire history of humanity. The transformation unfolds according to cosmic timescales measured in billions of years rather than centuries. But beneath that reassuring continuity, the direction of history has fundamentally changed. Every passing age now carries the universe toward greater closeness instead of greater separation. Expansion has surrendered its role, and the immense gravitational conversation between galaxies has begun speaking in reverse, one almost imperceptible step at a time. Across unimaginable ages, the spaces separating the largest structures in existence begin to shrink with growing certainty. Distances once measured in hundreds of millions of light years steadily contract until only tens of millions of light years remain between neighboring galaxy clusters. The pace still feels unhurried by human standards, yet the architecture of the universe is gradually reorganizing itself. The first encounters occur between entire clusters rather than individual galaxies. These immense collections of hundreds or even thousands of galaxies have long occupied their own gravitational domains, drifting through expanding space with little interaction, but contraction steadily draws them together. Their boundaries overlap, their gravitational fields intermingle. What had once been isolated islands become parts of something much larger. You might imagine catastrophic collisions between countless stars. The reality is more subtle. Galaxies consist mostly of empty space. Even when two large spiral galaxies pass directly through one another, individual stars are separated by such enormous distances that direct stellar impacts remain extraordinarily uncommon. The galaxies appear to crash, yet most stars continue their journeys without ever striking another star. But gravity transforms everything around them. As galaxies merge, their gravitational environments become increasingly chaotic. Stars are pulled onto entirely new orbits around freshly forming galactic centers. Vast clouds of hydrogen gas collide, compress, and collapse under their own weight. Those compressed clouds ignite waves of vigorous star formation, filling merging galaxies with brilliant clusters of newly born stars whose combined light reshapes the appearance of the heavens. During ordinary cosmic history, such mergers occur occasionally. In a contracting universe, they become unavoidable. Every galaxy belongs to the same long migration inward. No remote corner escapes participation. One merger feeds another, creating a cascading sequence extending across the observable universe as increasingly larger structures assemble from smaller ones. Imagine watching this process unfold from a stable planet, fortunate enough to survive these distant changes. The familiar darkness between galaxies would slowly disappear. Instead of scattered smudges of light resting far beyond one another, the sky would become crowded with luminous galactic cores approaching from every direction. Brilliant streams of stars would connect neighboring systems, while vast arcs of glowing gas stretched across the heavens would mark ongoing gravitational encounters. As contraction continues, galaxy clusters themselves merge into even greater assemblies. Those enormous superclusters, once separated by immense cosmic voids, begin converging as well. The largest known structures gradually lose their individuality. The intricate network of filaments and empty expanses that once defined the universe steadily compresses into a denser and more uniform arrangement. But this transformation remains incomplete. Distinct galaxies still exist, Although increasingly altered by repeated encounters, stars continue shining. New stellar generations continue forming inside compressed gas clouds. The universe has entered an era of relentless gathering, exchanging its once expansive pattern for one where matter accumulates ever more closely, preparing the cosmos for an environment unlike anything that has existed since its earliest beginnings. There comes an age when darkness itself begins to disappear. Across the contracting universe, the ancient background glow, left behind by creation, is steadily compressed into shorter wavelengths. What began as faint microwave radiation gradually shifts into infrared light, then continues climbing until visible light fills every direction you can imagine. At first, the change unfolds across spans of time so vast that no single civilization could notice it during its earliest stages. But the process never pauses. Every passing age packs the radiation into smaller wavelengths, increasing its energy throughout the entire cosmos. The universe itself is becoming warmer, independent of any individual star or galaxy. But this warmth comes from everywhere. The background of space gradually brightens until every direction shines with an intensity once found only near stellar surfaces. There is no longer any meaningful distinction between looking toward a star and looking into the open sky. Radiation arrives from every angle, bathing planets, moons, drifting clouds of gas, and the emptiness between galaxies in the same relentless glow. Worlds that once supported oceans cannot escape this transformation. Liquid water begins to absorb the ever-increasing radiation until seas slowly boil away. Rivers disappear. Lakes vanish. Water vapor rises into thick atmospheres that themselves become unstable beneath the growing energy surrounding them. Eventually, those atmospheres are stripped apart, molecule by molecule, leaving exposed planetary surfaces beneath an increasingly hostile sky. The final refuges disappear. Biological life depends upon delicate differences between warmth and cold, between incoming energy and outgoing heat. Those differences steadily vanish. Every surface receives nearly the same overwhelming radiation. Habitable environments cease to exist, not through sudden catastrophe, but through a universal rise in background energy that reaches every corner of space, without exception. But stars continue burning for a time. They still sustain nuclear fusion within their cores, converting lighter elements into heavier ones through immense pressure and temperature. Yet, stars survive only because they can release excess heat into surroundings that are cooler than themselves. That fundamental balance slowly begins to fail as the universe keeps heating from every direction. Eventually, the background temperature climbs towards stellar surface temperatures. It then rises beyond them. At that point, a star can no longer efficiently radiate its energy into surrounding space because its surroundings are no longer cooler. Heat has nowhere meaningful to flow. The normal exchange that allows stars to shine breaks down under the rules of thermodynamics, the branch of physics describing how heat moves from warmer regions toward cooler ones. The universe has changed completely. Space itself has become a furnace surrounding every remaining star. Their brilliant light no longer represents freedom for trapped energy. Instead, they endure inside a cosmos so intensely radiant that even these ancient engines of fusion can no longer function as they once did, enveloped by a universe that has become hotter than the fires that first illuminated it. For almost the entirety of cosmic history, every star has lived by maintaining an extraordinary balance. Gravity continually pulls matter inward, compressing the stellar core with tremendous force. Nuclear fusion answers that pressure by releasing energy outward, creating a stable equilibrium that allows a star to shine for millions, billions, or even trillions of years, depending on its mass. Throughout the long ages we have followed, that balance has defined every point of light across the universe. But the contracting cosmos slowly changes the rules. As the surrounding radiation grows hotter, stars lose the ability to release their own heat into space. Energy naturally flows from hotter places toward cooler ones. Once the background of the universe reaches temperatures comparable to stellar surfaces, that outward escape of heat steadily disappears. The star remains compressed by gravity, yet its normal method of maintaining equilibrium becomes increasingly ineffective. The consequences spread gradually. Stars begin expanding beyond their former stability. Internal layers grow turbulent as heat becomes trapped instead of escaping freely. Their structures become unstable in ways unlike ordinary stellar aging. This is not the familiar sequence that transforms stars through predictable stages of evolution. Instead, the surrounding universe itself has become hostile to the process that once allowed fusion to regulate stellar interiors. The most massive stars reach catastrophe first. Their enormous cores collapse under conditions that can no longer be sustained. Supernova explosions still erupt, releasing staggering amounts of energy and newly forged elements. Yet, these explosions no longer illuminate a comparatively cool universe. Their immense energy rapidly blends into the already brilliant radiation surrounding every galaxy, adding little distinction to a cosmos glowing almost everywhere at once. Smaller stars endure longer, although only briefly when measured against the immense history that created them. White dwarfs, the dense remnants left behind by stars similar to our own sun, gradually lose their identity as rising background radiation overwhelms the thermal differences that once defined them. Their stored heat no longer escapes in any meaningful way, and their remaining structure is steadily erased within the increasingly energetic environment. But some objects remain. Neutron stars survive because they are supported primarily by quantum mechanical pressure arising from the behavior of densely packed particles rather than ordinary thermal balance. Stellar black holes persist as well. They possess no surface that can be overheated in the familiar sense. Gravity has compressed them beyond every ordinary form of matter, leaving them largely indifferent to the thermal fate consuming everything around them. Across the observable universe, an estimated 1 septillion stars, roughly one followed by 24 zeros, vanish over a period astonishingly brief, compared with the countless billions of years required to create them. Their disappearance leaves behind black holes, neutron stars, scattered particles, and an ocean of intense radiation. The familiar universe that once nurtured galaxies, planets, and living worlds has faded into something almost beyond recognition, shaped by contraction rather than creation. Long after familiar cosmic landmarks have faded, a different hierarchy emerges. The countless stars that once defined galaxies have disappeared, leaving behind objects that neither intense radiation nor crushing temperatures can easily erase. We find ourselves entering an era ruled almost entirely by black holes, the deepest gravitational wells nature has ever produced. They remain. At the center of nearly every large galaxy rests a supermassive black hole, many containing millions or even billions of times the mass of our Sunday. As contraction steadily draws galaxies together, these immense objects are carried toward one another along with the remnants of their host systems. Their encounters unfold across millions of years before gravity finally binds them into orbit. But their dance cannot last forever. Each orbit sheds energy through gravitational waves, tiny distortions in the fabric of space and time itself that travel outward at the speed of light. You can imagine these waves as ripples spreading across an invisible cosmic surface, although they move through space and time rather than any physical material. Every revolution brings the black holes closer until they eventually merge into a single, even more massive object. One merger becomes many. Across the shrinking universe, similar unions occur again and again as galaxy after galaxy joins the collapse. Gravitational waves no longer arrive as isolated events. They overlap from countless directions, creating a persistent trembling that fills the entire cosmos. Space and time themselves never stand completely still, continually stirred by collisions unfolding across every region that still contains structure. Meanwhile, the surviving black holes continue growing. They absorb surrounding radiation, swallow drifting matter, and consume neighboring compact remnants. Every successful merger increases both their mass and the reach of their gravity. The contraction of the universe only strengthens this process, feeding ever larger concentrations of matter into already enormous gravitational traps. Boundaries begin to lose meaning. Distances separating neighboring black holes steadily shrink until their event horizons, the invisible surfaces beyond which nothing can escape, begin approaching one another. An event horizon marks the point where gravity becomes so overwhelming that even light cannot return. As more black holes merge, these boundaries expand, eventually overlapping with neighboring horizons to create vastly larger regions from which escape has become impossible. But one immense black hole spanning the entire universe has not yet formed. Instead, the ingredients are assembling through countless mergers, each one reducing the number of separate structures that remain. Diversity gives way to unity as gravitational collapse organizes the surviving mass into fewer and fewer colossal objects. The universe becomes simpler, although far more extreme than anything that existed during its earlier history. Black holes prove remarkably resistant throughout this transformation. Heat cannot burn them away. Radiation cannot dissolve them. They outlast stars, planets, and galaxies alike, becoming the final guardians of organized structure. Yet even these extraordinary survivors are not completely beyond the reach of the universe's final evolution. Their greatest challenge waits within the increasingly compressed cosmos itself. Imagine measuring the universe with a single number that steadily shrinks toward nothing. Cosmologists call this the scale factor, a mathematical description of the universe's overall size compared with earlier moments. During these final ages, that number continues falling until it approaches zero, marking a cosmos whose remaining distances are collapsing beyond ordinary comprehension. Everything compresses. Matter grows steadily denser, while radiation becomes increasingly energetic as every wavelength is squeezed shorter and shorter. Temperatures that required roughly 13,800,000,000 years to decline now race upward through the same range in only a tiny fraction of that history. Every stage of contraction unfolds faster than the one before, as gravity gathers strength from the universe's own increasing density. But acceleration now belongs to collapse. The surviving black holes, neutron stars, and oceans of radiation occupy a volume unimaginably smaller than the observable universe we once knew. Vast structures that previously stretched across enormous cosmic distances have vanished into an increasingly uniform concentration of energy and matter. The distinction between separate regions becomes harder to define because every remaining part of the cosmos is being forced toward every other part. General relativity guides us remarkably far. This theory describes gravity as the curvature of space and time created by mass and energy. It has predicted black holes, gravitational waves, and countless other phenomena with extraordinary precision. Yet, when its equations follow this contraction all the way to the end, they produce a singularity, a state where density becomes infinite and familiar measurements lose physical meaning. But infinity often signals incomplete understanding. Many physicists suspect nature avoids true singularities through processes that general relativity alone cannot describe. The problem appears when the universe reaches the Planck scale, the realm where distances become about 1.616 multiplied by 10 raised to the negative 35 power meters, and times shrink to roughly 5.39 multiplied by 10 raised to the negative 44 power seconds. At those extremes, gravity must obey quantum rules alongside everything else. No confirmed theory has crossed that bridge. Several competing ideas attempt to describe this hidden territory. String theory proposes that the smallest ingredients of reality behave like unimaginably tiny vibrating strands instead of point like particles. Loop quantum cosmology suggests that space and time themselves possess an underlying woven structure, preventing infinite compression. Both approaches offer intriguing possibilities, yet neither has received decisive experimental confirmation. We arrive at the frontier of knowledge. The equations that carried us across galaxies, through collapsing stars, and into merging black holes finally lose their certainty. Mathematics still points toward the end, although its guidance grows incomplete. But the final moments of a contracting universe unfold within a domain where every tested description of reality reaches its limit, leaving the closing chapter unwritten by any physics humanity presently possesses. Picture the remaining universe compressed until its entire contents occupy a region comparable to a single galaxy cluster. Every surviving remnant has been drawn into astonishing proximity, while contraction accelerates without pause. Distances that once required unimaginable spans of time to cross have almost vanished, leaving matter and radiation crowded into a realm where every passing moment deepens the collapse. Nothing escapes compression. Temperatures have climbed beyond trillions of degrees Kelvin. Those values exceed the fierce interiors of the most massive stars that ever burned across cosmic history. Radiation dominates every direction, and particles collide with energies impossible during the long eras when galaxies flourished. The distinction between ordinary environments and extreme ones has disappeared because every location now exists under conditions once found only during the universe's earliest moments. But matter itself begins to surrender. Atomic nuclei, which endured since the brief period of primordial element formation after the beginning of cosmic expansion, can no longer remain intact. The tremendous energy surrounding them tears apart protons and neutrons until they dissolve into their deeper constituents. The universe returns to a quark-gluon plasma, a state in which quarks and gluons move freely instead of remaining locked inside familiar particles. The transformation carries profound symmetry. This exotic plasma filled the cosmos during the first tiny fractions of a second after the beginning. Now, at the opposite end of cosmic history, contraction has reconstructed almost identical conditions. The immense journey from simplicity to galaxies, stars, planets, and living observers has folded back upon itself, restoring the universe to a state resembling its earliest chapter through an entirely different path. But gravity continues tightening its grip. Black holes, which inherited the collapsing cosmos long ago, still dominate the remaining structure. They are surrounded by matter and radiation packed so densely that the ordinary meaning of an event horizon becomes increasingly uncertain. An event horizon is the boundary beyond which nothing, including light, can escape a black hole. Yet under these extraordinary conditions, the surrounding universe itself approaches comparable extremes, blurring distinctions that once appeared absolute. Even quantum effects yield ground. Hawking radiation, the faint quantum process through which isolated black holes are expected to lose energy over immense spans of time, becomes completely overwhelmed. Instead of slowly shrinking, every black hole absorbs the relentless torrent of surrounding matter and radiation. Growth replaces evaporation because the inward flood vastly exceeds any outward quantum leakage. Everything falls together. Separate objects lose their identities beneath overwhelming density, relentless temperature, and unstoppable gravity. Every surviving particle, every wave of radiation, and every immense black hole shares the same direction of motion. We have reached a universe where collapse is no longer one process among many. It has become the only process that remains. There comes a stage where familiar imagination can no longer keep pace with reality. During the final second, every remaining fraction of cosmic history unfolds under conditions so extreme that ordinary experience offers no useful comparison. Space continues contracting, time carries events forward, yet the mathematics describing both approach their most demanding limits. Everything converges. The entire mass and energy contained within the observable universe has been compressed into a region smaller than a proton. Ordinary matter alone contributes roughly 1 multiplied by 10 raised to the 53 power kilograms, while dark matter and radiation add even more to the total. A proton itself measures only about 0.85 femtometers across, equal to approximately 0.85 multiplied by 10 raised to the negative 15 power meters. Every surviving structure has vanished into that astonishingly tiny domain. Density becomes overwhelming. Temperature climbs toward the Planck temperature, roughly 1.416 multiplied by 10 raised to the 32 power degrees Kelvin. According to present understanding, no higher temperature can be meaningfully described using established physics. Every particle carries extraordinary energy, while collisions occur under conditions beyond anything recreated inside the most powerful laboratories humanity has ever built. But another transformation may now unfold. The four fundamental forces governing nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are predicted by several theories to reunite into one underlying interaction. These forces normally appear distinct because the universe has spent immense ages cooling after its beginning. Under these unimaginable temperatures, those differences may disappear, revealing a deeper symmetry hidden beneath the familiar laws governing stars, atoms, and light. The pattern reflects the earliest beginning. During roughly the first 1 multiplied by 10 raised to the negative 43 power seconds after the beginning of cosmic expansion, many physicists believe this unified interaction separated into the individual forces shaping the universe we know. If contraction truly reaches the same physical conditions, that separation may reverse. The closing instant of cosmic history would resemble its opening instant with astonishing precision. But resemblance does not guarantee understanding. Every equation carrying us toward this point begins producing infinities instead of meaningful predictions. In physics, an infinity is rarely accepted as a literal feature of nature. It usually signals that the mathematical framework has reached the edge of its usefulness and cannot continue without a deeper description. General relativity, so successful across galaxies and black holes, finally encounters a boundary it cannot cross alone. We arrive before the final unknown. Whether a true singularity forms, whether quantum gravity prevents complete collapse, or whether reality transforms into something no present theory anticipates, remains unanswered. At the final second, every tested law still guides us remarkably close. Yet the very last step belongs to a realm where knowledge yields to possibility, and the universe keeps its deepest outcome beyond the reach of every equation humanity presently possesses. Our journey has followed the fate of the observable universe, yet that familiar phrase carries an important limitation. The observable universe is about 93 billion light years across, describing only the region whose light has had enough time to reach us since cosmic expansion began. Beyond that horizon, reality may continue for distances we cannot directly explore. The unseen may be vastly larger. During the earliest moments of cosmic history, a brief episode called inflation expanded space at extraordinary speed. Inflation refers to a rapid swelling of space itself, occurring before ordinary expansion settled into the slower evolution we measure today. If that process unfolded as current theories suggest, then the entire universe could extend far beyond everything our telescopes will ever observe. But nobody knows its true size. Some models describe a cosmos many orders of magnitude larger than the observable region. Others allow the possibility that space has no edge at all, continuing without limit. Because light from those remote domains has never reached us, and perhaps never will, direct measurement remains impossible despite remarkable advances in astronomy. An enormous universe allows remarkable possibilities. If matter and energy were distributed with slight differences across unimaginably vast distances, some regions might evolve along paths unlike our own. A particularly dense domain could eventually halt its expansion and begin collapsing while distant regions continue expanding. In that picture, a big crunch would no longer represent the fate of every corner of existence. It would become the destiny of one immense neighborhood within a far larger reality. But such a collapse would remain hidden. As space changes, light must still travel across it to carry information. If a distant region contracts rapidly enough, its final signals could never escape toward us. The collapse would unfold beyond every future observation, sealed behind the geometry of space itself rather than by any physical barrier. This idea naturally connects with multiverse concepts. Within several modern cosmological frameworks, different regions of the greater universe may possess different initial conditions established during inflation. Those differences could influence expansion, density, and long-term evolution, allowing widely separated domains to follow independent histories. Some might expand forever, while others eventually reverse course. The possibility changes our perspective. Instead of imagining one universal ending shared by every star and galaxy, we begin considering countless cosmic histories unfolding beyond our horizon. Some regions may never experience contraction. Others may have completed that journey long before our own galaxies formed. We cannot confirm such possibilities with present observations, yet they remain mathematically consistent within several theoretical models. But the horizon keeps its secrets. Everything we have measured belongs to one visible island within a potentially far greater ocean. Whether distant realms have already collapsed, continue expanding, or follow entirely different destinies remains beyond the reach of light, leaving the ultimate geography of the universe one of cosmology's deepest, unanswered questions. For much of this journey, we have followed a universe that begins once and ends once, but another possibility has lingered beside that picture for decades, offering a profoundly different rhythm. Instead of a single cosmic lifetime, existence may unfold through repeated cycles separated by extraordinary transitions rather than absolute beginnings. One proposal is called the ekpyrotic model. The name comes from an ancient Greek idea describing renewal through fire, although the modern theory is rooted in advanced mathematics rather than mythology. In this framework, the event we call the Big Bang was never the ultimate beginning of space, time, or reality. It marked a dramatic encounter between far larger structures already existing beyond our familiar universe. Those structures are known as membranes. A membrane, often shortened in technical discussions, is a three-dimensional cosmic surface that can exist within a higher dimensional space, predicted by some versions of string theory. According to this idea, everything we experience, every galaxy, every star, and every particle remains confined to one such membrane, while additional dimensions extend beyond our perception. But our membrane may not be alone. The ekpyrotic picture imagines another parallel membrane drifting through the higher dimensional landscape. Across unimaginable spans of time, gravity gradually draws these enormous structures together. When they finally collide, astonishing amounts of energy are released. That energy fills the membrane with intensely hot matter and radiation, producing conditions that resemble the earliest moments traditionally attributed to the Big Bang. The collision becomes the beginning we observe. As the membranes separate again, the expanding universe evolves much as conventional cosmology describes. Galaxies form, stars ignite, heavy elements emerge, life eventually appears on suitable worlds. Yet beneath that familiar sequence, the larger cycle continues as the membranes slowly move apart before beginning another long approach. But the cycle never truly ends. Within this interpretation, a future big crunch does not represent permanent extinction. Instead, contraction prepares the conditions for another collision. The apparent ending becomes a boundary between one cosmic era and the next, allowing a fresh expansion to emerge without requiring creation from absolute nothingness. This modern cyclic version was developed by Paul Steinhardt and Neil Turok during the early years of the 21st century. They proposed it as an alternative to inflation, the widely accepted idea that the infant universe expanded extraordinarily rapidly during its earliest fraction of a second. Both frameworks successfully explain many observed features of the cosmos, making direct comparison remarkably difficult. But evidence remains elusive. Many measurable predictions overlap so closely that even our most advanced observatories cannot yet distinguish one scenario from the other with confidence. For now, both remain serious subjects of theoretical investigation, reminding us that cosmology still contains profound uncertainties. The Big Crunch may be the final chapter of one universe, or it may simply mark the instant when another cosmic story begins to unfold. Imagine reaching a destination where every trusted equation suddenly loses its footing. We have followed gravity through collapsing galaxies, fading stars, and overwhelming densities. But at the smallest conceivable scales, another possibility begins to emerge, suggesting that the universe may refuse to compress forever. This idea is called loop quantum cosmology. Loop quantum cosmology is an attempt to unite quantum mechanics, the science governing the smallest particles, with the geometry of spacetime itself. Instead of treating space as perfectly smooth, the theory proposes that spacetime possesses an underlying granular structure, built from unimaginably tiny units that cannot be divided without limit. That assumption changes everything. Within general relativity, the Big Crunch ends at a singularity, a point where density becomes infinite and the mathematics ceases to produce meaningful physical predictions. A singularity signals that the theory has reached the edge of its usefulness rather than proving that nature truly contains infinities. Loop quantum cosmology offers another path. According to this framework, space-time has a smallest possible unit of area, commonly called the Planck area. Once the universe contracts to that fundamental scale, further compression becomes impossible. Instead of allowing density to increase forever, quantum effects become overwhelmingly powerful and alter gravity itself. But gravity no longer acts alone. A new repulsive behavior emerges from the quantum properties of spacetime. Some researchers describe this mathematically as a quantum bounce pressure, meaning an effective resistance created by quantum geometry rather than an ordinary physical force. As density climbs toward the ultimate limit, that repulsive effect strengthens until collapse finally stops. Then the direction changes. Rather than ending in an unreachable singularity, the universe rebounds into expansion. This event is known as the Big Bounce. The immense compression becomes the starting point for another cosmic era, transforming contraction into a new beginning without requiring an absolute creation event. Within these models, our own expanding universe may already be the descendant of an earlier collapsing cosmos. The Big Bang would represent a transition instead of an origin, carrying the history of one universe into the birth of another through a process governed by quantum geometry. But profound mysteries remain. No one yet knows whether information survives such a bounce. Could the values of fundamental constants persist? Might traces of ancient structure influence the next expansion? Does entropy, the measure of disorder, reset completely or pass through an altered form? These questions remain unanswered because current mathematics cannot yet provide definitive solutions. Much of the modern development of these ideas has been led by Abhay Ashtekar and colleagues at Pennsylvania State University, who constructed detailed mathematical descriptions showing how a bounce can naturally replace a singularity under specific assumptions. Even so, no observation has confirmed this remarkable picture. Our instruments cannot yet probe conditions so extreme, leaving the Big Bounce suspended between elegant mathematics and the vast unknown that still surrounds the deepest origins of the cosmos. Another possibility begins from an unexpected place, not with collapse, but with endless expansion carried to its ultimate conclusion. We have explored futures where gravity gathers everything inward. Roger Penrose invites us to consider whether an eternally expanding universe might also circle back to a new beginning through mathematics alone. His proposal is called conformal cyclic cosmology. Roger Penrose, awarded the Nobel Prize for his work on black holes and gravitation, argues that the unimaginably distant future may gradually erase the very concept of physical scale. Long after every familiar structure has disappeared, the universe would continue changing in subtle but profound ways. The transformation takes extraordinary time. According to this picture, ordinary matter eventually vanishes. Massive particles either decay through processes predicted by some theories beyond the current standard model of particle physics, or they become trapped inside black holes. Even those black holes do not survive forever. Through Hawking radiation, the quantum process proposed by Stephen Hawking, black holes slowly release energy and lose mass until they ultimately disappear. But something remains. Only particles without mass continue onward, chiefly photons and hypothetical gravitons, the proposed carriers of gravity in quantum theories. Massless particles experience spacetime differently from objects with mass. From the perspective described by relativity, a photon does not experience the passage of time along its path between emission and absorption. That detail changes the mathematics. When every remaining particle is massless, absolute size loses physical meaning. Without rulers made from matter or clocks carried by massive particles, a universe expanded to an almost unimaginable scale can be transformed mathematically into one that is arbitrarily small. This transformation is called conformal rescaling, meaning shapes and relationships are preserved while overall scale becomes irrelevant. But the story does not stop there. Penrose proposes that this rescaled future can be identified with the beginning of a new cosmic age. Each complete history is called an aeon. In this framework, the Big Bang was not the creation of everything. Instead, it formed the boundary separating our aeon from an older one whose black holes had already faded away. This vision suggests continuity without repetition. Each aeon develops independently, yet every ending naturally becomes the starting condition for the next. No crushing singularity is required. No bounce through extreme density is necessary. The universe simply passes across a mathematical bridge, connecting one immeasurably old expansion to another. Penrose has gone further by suggesting that traces of the previous eon may still be visible today. He and collaborators have reported circular features within the cosmic microwave background, known as Hawking points, which they interpret as possible remnants of evaporating black holes from the preceding aeon. But the evidence remains deeply contested. Many cosmologists argue that these patterns arise naturally from statistical fluctuations rather than ancient cosmic history. Current observations have not settled the debate, leaving conformal cyclic cosmology as one of the most imaginative and mathematically sophisticated possibilities in modern theoretical physics. After exploring possibilities that stretch far beyond direct observation, we arrive at the measurements available today. Everything we have imagined ultimately returns to evidence, gathered patiently by telescopes that map light arriving from across cosmic history. We cannot yet witness the universe's final fate, but we can examine the clues already reaching us. The picture remains remarkably precise. The European Space Agency Planck satellite produced the most detailed map of the cosmic microwave background ever obtained. Those measurements indicate that the geometry of the observable universe is extremely close to perfectly flat, with the density parameter remaining extraordinarily close to 1. Such a result agrees comfortably with endless expansion, although it does not completely eliminate the possibility of a slight excess of matter that could eventually alter the universe's long-term evolution. But another experiment has introduced fresh uncertainty. In April of 2024, the Dark Energy Spectroscopic Instrument Collaboration released its first year of cosmological results after constructing the largest three-dimensional map of the universe ever assembled. The survey analyzed nearly 6 million galaxies and quasars, tracing more than 11 billion years of cosmic expansion with unprecedented precision. The most intriguing result concerns dark energy. Cosmologists often describe its behavior using an equation of state parameter, a mathematical quantity expressing how dark energy changes as the universe evolves. If that value never changes, cosmic acceleration continues indefinitely. But the dark energy spectroscopic instrument measurements hint that dark energy may instead weaken over time, suggesting the force driving expansion was stronger in the distant past than it appears today. That possibility changes everything. A weakening dark energy would gradually surrender influence to gravity. Expansion could slow. Under certain future conditions, contraction might once again become possible. Yet the statistical significance remains below the level required for a scientific discovery. Additional observations are essential before anyone can claim that this subtle pattern reflects reality rather than chance. More answers are already on their way. The Vera Rubin Observatory will survey hundreds of millions of galaxies, measuring how cosmic structure grows across immense distances and refining our understanding of dark energy. The Nancy Grace Roman Space Telescope will conduct extensive observations of distant Type 1, a supernovae, stellar explosions that serve as remarkably consistent distance markers, allowing astronomers to measure the expansion history of the universe with even greater accuracy. But the most important conclusion is wonderfully simple. The fate of the universe has not been decided by philosophy, speculation, or elegant mathematics alone. It remains an experimental question. Every new observation has the power to strengthen today's picture or overturn it entirely. As we continue measuring the deepest reaches of space, you and we are living during the first era when humanity can genuinely test how the cosmos may ultimately end. Imagine arriving in a universe already moving toward collapse, yet finding nothing around you that immediately reveals its destiny. Galaxies would still decorate the heavens, stars would continue shining, and planets could remain suitable for oceans, weather, and living ecosystems. If you measured only your local surroundings, you might conclude that everything looked wonderfully familiar. The deeper change would unfold beyond ordinary experience. For billions of years after the Great Turnaround, contraction would remain almost impossible to detect without extraordinarily precise cosmological observations. A civilization living 50 billion years after the reversal could build observatories, develop mathematics, and explore nearby stars while remaining unaware that the overall expansion had already changed direction. Daily existence would continue almost unchanged, but the universe itself would slowly become the threat. The cosmic microwave background, the ancient radiation left from the earliest moments of cosmic history, would steadily gain energy as every wavelength compressed during contraction. Microwave radiation would shift into infrared light, then eventually into visible light, transforming empty space into an increasingly luminous environment. The danger would no longer come from individual stars. It would arrive from every direction at once. There would be nowhere to hide. Theoretical physicist Freeman Dyson once explored how intelligence might survive forever inside an endlessly expanding universe. His proposal suggested that advanced civilizations could gradually slow their metabolism, thinking ever more slowly while the surrounding universe continued cooling. Time would stretch, yet conscious experience could continue without an absolute ending. But contraction reverses every advantage. Instead of falling temperatures extending survival, the background radiation climbs relentlessly higher. Every interval of cosmic history becomes warmer than the one before it. Life cannot indefinitely reduce its energy needs when the environment itself grows increasingly hostile. The entire universe becomes a steadily heating habitat whose conditions move in only one direction. Astrophysicist Fred Adams and Gregory Laughlin examined the distant future of life under several cosmological possibilities in work published during the 1990s. Their analysis showed that a universe ending in a big crunch offers only a finite window for biology. The ultimate limit does not arise because every star exhausts its fuel first. It emerges because the rising radiation background eventually overwhelms every conceivable refuge. The boundary is absolute. No known physical process allows complex biological systems to remain stable once the surrounding radiation field reaches sufficiently extreme temperatures. Chemistry fails before gravity completes the final collapse. Biology disappears long before the universe approaches its last moments. But one final idea has occasionally appeared at the edge of theoretical discussion. Physicist Frank Tipler proposed the omega point theory, suggesting that immense computational processes might become embedded within the universe as collapse approached, allowing intelligence to persist in an extraordinary form. Most cosmologists reject this proposal because it depends upon assumptions unsupported by observation or accepted physical theory. Even so, it reflects a deeply human impulse. As we imagine the universe reaching its final horizon, we continue asking whether thought itself could accompany it to the end. Long before we ask how the universe might finish, we must ask a simpler question. What does time itself seem to prefer? Every spilled drop, every fading star, and every cooling ember follows the same profound tendency. Order gradually gives way to greater disorder, a principle known as the second law of thermodynamics, which states that entropy, a measure of the number of possible arrangements within a system, can only increase or remain unchanged in a closed universe. Everything we have seen obeys that rule. The earliest observable universe emerged in an astonishingly low entropy condition. Matter was distributed with remarkable uniformity, and although tiny fluctuations already existed, the cosmos possessed an extraordinary degree of large-scale order. Ever since then, gravity has gathered matter into galaxies, stars, and black holes, while the total entropy has continued climbing without exception. An expanding universe follows a familiar destination. As expansion continues forever, energy spreads across ever larger volumes of space. Temperatures fall, differences gradually disappear. Eventually, the universe approaches maximum entropy as an immense, cold, dilute expanse where little further change remains possible. This is the scenario often called heat death, a future defined by exhaustion rather than violence. But contraction changes the landscape. As space shrinks, radiation becomes hotter and matter grows increasingly compressed. At first glance, it may seem that squeezing everything together should reverse entropy itself. Yet compression alone does nothing of the sort. Unless every particle moves in perfectly coordinated fashion, disorder continues increasing even while temperatures soar and density climbs ever higher. The distinction matters greatly. A hypothetical big crunch would gather extraordinary entropy into an extraordinarily small volume. The final state could become almost perfectly uniform in temperature and density, yet it would still represent an enormously disordered configuration according to thermodynamic principles. The universe would resemble the beginning in heat and density, while remaining fundamentally different in its internal history. That difference creates a profound puzzle. Our own cosmic beginning appears to have possessed remarkably low entropy despite its incredible temperature. A big crunch, by contrast, seems destined to end with extremely high entropy. If a new expansion followed immediately afterward, why would the next universe not inherit all that accumulated disorder? Why would every successive cycle avoid becoming progressively more chaotic? No accepted answer exists. But several ideas attempt to bridge that gap. Roger Penrose proposed that conformal cyclic cosmology could remove the significance of scale after every black hole has completely evaporated through Hawking radiation, allowing entropy to be reinterpreted across the boundary between successive aeons. Whether nature truly behaves this way remains uncertain, yet the proposal confronts one of cosmology's deepest thermodynamic challenges directly. The arrow of time still points forward. Every observation we have gathered agrees with that direction. Whether the universe expands forever, contracts into a final collapse, or somehow begins anew, the mystery of entropy remains woven into every possible ending, reminding you and us that understanding the fate of the cosmos ultimately requires understanding time itself. We experience time so naturally that it feels impossible to question. Every memory lies behind us. Every expectation waits ahead. From childhood to old age, from sunrise to sunset, every moment appears to confirm that time possesses a preferred direction. Yet modern physics suggests something more subtle. The flow we experience may emerge from deeper physical processes rather than existing as a fundamental feature of reality. Entropy provides the strongest clue. As disorder increases, events become distinguishable from one another. Eggs break rather than spontaneously reassemble. Stars exhaust their fuel instead of growing younger. Information spreads into ever greater numbers of microscopic arrangements. This persistent increase in entropy creates what physicists call the arrow of time, the apparent distinction between past and future that shapes every experience we have. Expansion has always accompanied that process. Throughout cosmic history, new structures formed while overall entropy continued rising. Galaxies assembled, stars ignited, planets cooled, and life emerged without violating the second law of thermodynamics. Local pockets of increasing complexity developed because the total disorder of the universe continued growing even faster. But contraction changes the setting, not the rule. A universe shrinking toward a big crunch would still contain local entropy gradients, meaning neighboring regions differ in energy and organization. Chemistry would continue operating normally. Biological evolution would remain forward moving. Thoughts would still follow memories rather than anticipate them. A civilization living during contraction would experience yesterday, today, and tomorrow exactly as you and we understand them now. Time would still seem familiar. Science fiction often imagines a collapsing universe, forcing every event to unfold backward. Rivers would climb mountains, broken glass would leap together, and conversations would reverse into unspoken thoughts. Modern physics offers no convincing reason to expect such extraordinary behavior. The large-scale motion of the cosmos does not automatically reverse local thermodynamic processes, yet the deepest stages may challenge even that confidence. Some physicists have suggested that if collapse approached an almost perfectly symmetric state, the conditions defining a clear direction of entropy could gradually disappear. Without meaningful entropy gradients, the distinction between before and after might lose physical significance. Causality, the relationship in which one event produces another, could itself become difficult to define using existing theories. This possibility reaches beyond ordinary intuition. Physicist Julian Barbour has explored models in which time is not a fundamental ingredient of the universe at all. Instead, what we perceive as a flowing present may arise, statistically, from changing physical configurations. According to that perspective, time resembles an emergent pattern rather than an invisible river carrying everything forward. But the Big Crunch pushes every such idea to its limit. If the final collapse eventually erases the entropy differences that distinguish one moment from another, it may also erase the physical conditions that allow time to possess meaning. At that boundary, the question may no longer be whether time continues. The deeper question becomes whether time was ever fundamental in the first place. Imagine gathering every event that has ever unfolded into a single invisible ledger. Every collision between particles, every heartbeat, every thought, every photon that crossed empty space would contribute another line. Physics gives that ledger a name. It is called information, meaning the complete description of every physical state that has ever existed. As our journey approaches its deepest question, we discover that preserving information may matter even more than preserving matter itself. Quantum mechanics rests upon a principle known as unitarity, the idea that information is never truly erased from reality. Physical systems may change into forms beyond recognition, yet the complete description of those changes should remain recoverable in principle. Hidden does not mean destroyed. Scrambled does not mean forgotten. But singularities challenge that confidence. For many years, Stephen Hawking argued that black holes permanently erased information falling beyond their event horizons. Such a loss would violate unitarity and overturn one of quantum theory's central foundations. After decades of debate and new theoretical developments, he publicly revised his position during the year 2004, concluding that information should ultimately survive, although recovering it could remain unimaginably difficult. That debate now expands to its greatest possible scale. If an entire universe collapses into a final singularity, every quantum interaction since the beginning becomes part of the same question. Every particle state, every field fluctuation, every galaxy, every living organism, and every moment of history would converge toward a single mathematical boundary. Could anything preserve such overwhelming complexity? General relativity offers little comfort. Within that framework, a singularity marks the point where space-time itself ceases to provide meaningful answers. Physical quantities become infinite, equations lose predictive power, and the mathematical description ends. If the theory is taken literally, information reaching that boundary possesses no defined future. But quantum gravity may tell another story. No complete theory yet exists to unite quantum mechanics with gravitation under these extreme conditions. Until such a framework is discovered, we cannot determine whether information disappears, transforms, or remains encoded in ways current mathematics cannot yet describe. One remarkable possibility comes from the holographic principle, developed through the work of Gerard Hooft and Leonard Susskind. This idea proposes that all information contained within a volume of space could instead be represented upon its surrounding boundary, much as a flat surface can encode the appearance of depth. The boundary becomes the essential record. If that principle remains valid during ultimate collapse, the interior may compress beyond recognition, while the complete informational history persists along the evolving boundary of spacetime itself. But certainty ends there. The Big Crunch, therefore, represents far more than the collapse of matter and energy. It becomes the greatest information problem in all of physics. Whether any pattern, memory, or record survives beyond that final limit remains one of the deepest unanswered questions ever placed before human understanding. Across almost the whole history of the cosmos, distance has acted like an editor, deciding which stories could ever reach us. Every beam of light carried news from somewhere else, yet countless messages remained forever beyond our horizon as space stretched between galaxies. We have traveled beside that growing separation for billions of years, but the direction has now changed. The contraction slowly redraws the map. Galaxies that vanished beyond one another's observable horizons begin returning to view. Horizons, meaning the limits beyond which light can no longer reach an observer, gradually shrink instead of expanding outward. Regions once permanently disconnected become linked again through converging spacetime. Separation gives way to reunion. An extraordinary exchange begins. Light released billions of years earlier finally completes journeys that once seemed impossible. Ancient stars reveal their last moments. Long vanished galaxies return through the arrival of forgotten photons. If civilizations ever existed within those distant systems, the signals they released into space, whether intentional broadcasts or ordinary flashes of technology, would also continue traveling until contraction carried them home. But none of those civilizations remain to receive replies. The universe becomes a place where every unanswered message eventually arrives, although its sender may have disappeared beyond imagination long before. Cause and effect remain intact. Time still moves forward for every observer, yet history folds inward until records, once scattered across unimaginable distances, gather into the same shrinking cosmic volume. There is a strange completeness in that convergence. We often imagine the end of the universe as increasing loneliness. A contracting cosmos offers another possibility. During its final ages, it grows progressively more connected. Every surviving observer gains access to light, that expanding space once concealed forever. The visible universe becomes richer even as its future grows shorter. But this reunion cannot last. As compression continues, the background radiation rises across every wavelength. Gentle microwave radiation steadily shifts toward infrared light, then visible light, then increasingly energetic forms of radiation. Each arriving message must travel through a cosmos, becoming brighter, hotter, and more chaotic with every passing interval. Eventually, distinction begins to disappear. Individual signals become harder to separate from the surrounding radiation. The information carried by each photon remains present in principle, yet extracting any meaningful pattern becomes increasingly impossible within the overwhelming thermal environment. Contrast fades. Structure dissolves. The universe continues collecting every remaining messenger, every reflected glimmer from ancient worlds, every pulse from dying stars, every wandering photon released across cosmic history joins the same inward current. For one remarkable span, the collapsing cosmos gathers nearly everything it once scattered. But the rising radiation permits no lasting archive. The final approach transforms every surviving message into part of one immense, uniform roar, where signal and background become physically indistinguishable, and the universe completes its last great act of listening. Suppose, for one final thought experiment, that something capable of processing information could remain aware almost until the universe reached its ultimate limit. We are no longer imagining human eyes or human senses. We are imagining the last possible witness allowed by physics, following reality as far as known laws permit. The sky has ceased to resemble a sky. Every direction glows with overwhelming radiation produced by the compression of everything that once occupied the observable universe. Individual stars cannot be distinguished. Galaxies have long since disappeared into the growing brilliance. There is no darkness between objects because there are no separate objects left to frame against darkness. Every line of sight meets the same blazing wall. But light is only part of the experience. Gravitational waves, meaning ripples traveling through the fabric of space-time itself, sweep across every remaining region as countless black holes merge into larger and larger structures. The distortions never pause. Every location trembles continuously because every massive concentration contributes to the same collapsing geometry. Motion and gravity become inseparable. The familiar boundaries also disappear. An event horizon marks the surface beyond which nothing can escape a black hole. During these closing stages, neighboring event horizons overlap until separating one black hole from another loses physical meaning. The distinction between inside and outside gradually fades because space-time itself no longer provides stable borders between them. Everything converges. The complete history of nearly 14 billion years, from the earliest clouds of hydrogen through the birth of galaxies, planets, living worlds, and every civilization, occupies a region smaller than any ordinary intuition can represent. Scale itself ceases to guide understanding. Distances no longer provide meaningful separation between events once divided by unimaginable expanses. But where does the observer stand? That question slowly dissolves with the collapsing universe. There is no distant platform from which reality can be surveyed. The observer exists within the same shrinking spacetime, undergoing compression. As the remaining volume approaches its final limit, observer and universe become impossible to distinguish as separate systems. There is no external audience. There is only participation. One interval remains beyond this description. The final Planck moment, lasting approximately 1/10,000 trillionth of a trillionth of a second, represents the shortest meaningful interval predicted by known physics. Beyond that duration, our current theories lose the ability to describe spacetime reliably. General relativity and quantum mechanics, each extraordinarily successful in their own domains, no longer provide a complete account together. But honesty becomes the most important scientific tool. We can calculate the approach. We can trace the collapse with astonishing precision, yet the final instant remains hidden behind the limits of human knowledge. The last fraction of existence is not filled with certainty. It is defined by the place where every successful equation finally reaches its edge. Step outside our familiar sense of history for a moment, and the scale changes completely. The universe has existed for about 13.8 billion years. Modern humans have existed for roughly 300,000 years. Against the full span of cosmic history, our presence occupies only the thinnest fraction of the story. Picture the entire lifetime of the universe compressed into a single calendar year. The first expansion unfolds at the opening moment of the first day. Galaxies gradually emerge. Stars ignite, evolve, and enrich space with heavier elements. Planets assemble around younger suns. Life becomes possible only after countless generations of stellar birth and death have transformed the raw material of the cosmos into something more complex. Then, almost at the very end, we appear. Humanity enters during approximately the final 12 minutes before midnight on the last day of that imagined year. Every civilization, every discovery, every language, every work of art, every telescope pointed toward the sky belongs within those closing moments. Our entire recorded history occupies only the last few seconds, but even that astonishing brevity may still arrive remarkably early. Some compressed cosmological models allow the universe to reverse from expansion into contraction after only a few billion more years. That remains speculative, yet it provides an interesting comparison with our own planet's future. Long before any possible cosmic collapse begins, the increasing brightness of the sun is expected to heat Earth until its oceans gradually disappear, approximately 1 billion years from now. The home that shaped our species reaches its practical limit well before the universe approaches its own. Our horizon is smaller. That realization gives our place in time an unexpected character. We exist early enough to recognize the question of the universe's fate, yet far too early to determine its answer through direct observation. We measure clues instead. We compare theories. We refine instruments. Each generation extends the reach of the previous one. But the universe surrounding us also occupies an unusual chapter. Stars still shine across enormous galaxies. New stars continue to form from vast clouds of gas. Heavy elements remain available to build rocky worlds. Conditions capable of supporting chemistry, biology, and eventually, observers have not vanished. Complexity flourishes across many different scales, from living cells to galaxy clusters. Nothing guarantees that this era represents an ordinary moment within the complete lifetime of the cosmos. The anthropic principle offers one possible perspective. It proposes that we observe a universe compatible with our existence, because only such a universe can produce observers capable of asking these questions in the first place. That idea does not place humanity at the center of space or time. Instead, it reminds us that our presence is one consequence of the universe evolving exactly long enough and in exactly the right ways for curiosity itself to become part of its unfolding story. Long before telescopes measured distant galaxies, people stood beneath the night sky and searched for the same answer. Does anything endure? Every civilization framed that question differently, yet the longing beneath it remained remarkably familiar. We have inherited both the question and the tools to examine it, even though neither offers certainty. The Big Crunch presents one possible reply. Everything that formed across cosmic history would ultimately return through overwhelming compression. Stars, galaxies, black holes, planets, memories encoded in living brains, and every structure assembled over billions of years would lose their separate identities as the universe approached its final state. Nothing escapes that convergence. Nothing remains apart. But physics reaches a natural boundary there. Whether impermanence diminishes meaning belongs to another conversation entirely. Equations describe how matter behaves under extraordinary conditions. They cannot determine whether a life was worthwhile or whether beauty depends upon permanence. Those questions emerge wherever conscious beings reflect upon their own existence, regardless of the universe surrounding them. Many ancient traditions wrestled with remarkably similar ideas. The Stoic philosophers imagined that reality periodically returned to a primordial cosmic fire before beginning again. Their vision arose more than 2,000 years before modern cosmology, yet its rhythm echoes surprising aspects of cyclic universe models. They reached that picture through philosophical reasoning rather than observation, searching for order within change. Buddhist cosmology also describes immense cycles known as kalpas, unimaginably long eras during which universes emerge, evolve, dissolve, and begin anew. These cycles extend across timescales so vast that ordinary human history becomes almost impossible to perceive within them. The language differs from physics, yet both perspectives invite us to think beyond the span of individual civilizations. But modern science asks different questions. Rather than searching for purpose, it searches for evidence. Theoretical models compete, observations improve, old ideas are discarded when nature refuses to support them. That spirit appears beautifully in the words of physicist Richard Feynman, who once said that he would rather have questions that cannot be answered than answers that cannot be questioned. Those words remain a reminder that uncertainty is not failure. It is often the beginning of deeper understanding. The Big Crunch can almost seem like the universe, turning inward upon itself, gathering every chapter into a single unresolved ending before the final page can ever be read. Whether that image reflects physical reality remains unknown, yet it captures something enduring about our search. We have built observatories, equations, stories, and civilizations. We have wondered where we came from and how everything might end. Those acts of curiosity happened. They became part of the universe's history simply because the universe produced beings capable of asking. Whether the cosmos preserves every trace belongs to physics. Whether those moments mattered remains a question that only we can continue to explore. Tonight, while you look upward, the universe continues a story already about 13.8 billion years old. It unfolds without pause, carrying galaxies farther across space, igniting new stars, extinguishing old ones, and shaping futures that no observer can yet describe with certainty. We stand within that unfolding, able to witness only a brief chapter. Everything we have explored has led us here. Every telescope raised above Earth's atmosphere, every detector buried beneath mountains, every mathematical insight patiently tested against observation represents the same enduring effort. We are trying to read the final page of a book while countless chapters are still being written. We collect fragments, compare patterns, and slowly reduce uncertainty. But the ending remains beyond our reach. Several endings remain possible. Dark energy may continue driving expansion almost exactly as it does today. If that picture proves correct, the universe will keep growing larger and colder across unimaginable spans of time, drifting toward an era where stars gradually disappear and warmth becomes increasingly rare. But another possibility has never completely vanished. If dark energy changes, if the balance of cosmic density ultimately shifts, expansion could someday give way to contraction, and every galaxy, every black hole, and every particle would begin the long return toward a common destination. We simply do not know. That uncertainty is one of science's greatest strengths. Knowledge advances by allowing evidence to decide which ideas survive. Questions remain open until nature provides an answer, even when that answer takes generations to uncover. Our willingness to live beside uncertainty has revealed more about the universe than certainty alone ever could. Meanwhile, the cosmos continues regardless of our understanding. Somewhere within the observable universe, a cloud of hydrogen that has drifted since the earliest moments after the Big Bang is collapsing under gravity, beginning the life of another star. Somewhere else, an ancient star has exhausted its fuel, returning its enriched elements to space, preparing material for worlds that do not yet exist. Creation and ending proceed together across the sky, woven into the same vast process. The story never pauses. It does not wait until we solve every equation or resolve every debate. It unfolds whether we are watching or not, carrying us with it through an immense history that may continue forever, or may someday close through unimaginable compression. Both possibilities remain alive within modern cosmology, but one fact already belongs to the universe beyond dispute. Across billions of years of expanding space, matter organized into stars, planets, living cells, curious minds, and eventually into us. We became the small part of the cosmos capable of wondering where it came from, where it is going, and what any of it means. Whatever ending ultimately awaits, that moment of awareness has already happened. We are the universe reflecting upon itself, and for now, that is enough.